So for my spec point 15.13, I'm going to be looking at acyl chlorides, nomenclature and formulae. I'm also going to be looking at esters. Sharvis is going to be looking into the reactions of acyl chlorides, and then Niall is going to be looking at hydrolysis of esters, and he's going to be talking all about polyesters. So first of all, an acyl chloride is derived from a carboxylic acid, but instead of having the functional group COOH, which is the normal functional group of a carboxylic acid, you're going to replace the hydroxyl group with a chloride atom. Therefore, the acyl chlorides have general formula RCOCl, where R is a side chain. For this topic, you need to know how to write the structural formula of an acyl chloride, draw the displayed formula, and draw the skeletal formula. So first of all, structural formula. That should be easy for everyone, it's just basics. So for ethanoyl chloride, you have CH3COCl. For propanoyl, because it's got 3 carbons, it's gonna be C2H5COCl. And then for butanoyl chloride, you're gonna have C3H7COCCl. Now let's look at displayed and skeletal formulae. So as you can see, it's pretty straightforward, nothing too complicated. But for skeletal formula, just remember that you never include the carbon group and you never include the hydrogen group. You only include the bonds and the atoms that are different from carbon and hydrogen. Now let's have a look at esters. These are derived from acids where at least one OH group is replaced with an O alkyl group. Esters consist of alkyl groups attached to O atoms and carbon atoms. They have the general formula RCOOR, and then there's like an apostrophe at the top, where R can be a hydrogen atom or an alkyl group, and the other R is an alkyl group but not a hydrogen atom. Just to remind you from last year, the general formula of an alkyl group is CnH2n+1. Naming esters. Esters are made up of 2 names. The first word is for the alkyl group joined to an O atom, and the second word is for the alkyl group joined to a C atom. Obviously the structural formulae, these are not too difficult to learn, again it's just basics. For displayed formulae, as you can see for the first one, we have methyl methanoate. So the methyl represents the CH3 atom at the right, so that's an alkyl group. And then as you can see, the methyl group is attached to an oxygen, and then the oxygen is attached to this special functional group. You're gonna see this repeating pattern of a C with a double bond O. Since there is only one C, then we say it's methanoate. For the second example, we've got a methyl group, so that remains the same, but because there's 2 C's on the left of the oxygen atom, then it becomes ethanoate. And then you just repeat the same idea for the rest of the elements. For the skeletal formula, just to reiterate, just all you have to do is to remove the carbon and hydrogen atoms and keep the bonds as they are and include all the rest of the elements. And yeah, you should be fine.
So as Yasser said, acyl chlorides contain a COCl group. These make acyl chlorides very reactive, and so they can react with a wide range of molecules. For this part, we need to know about 4 specific reactions. So acyl chloride with water, acyl chloride with alcohol, acyl chloride with ammonia, and acyl chloride with amines. For all of these, you don't have to know the reaction mechanisms. You just need to be able to do the displayed formula or the structural formula. And remember that I said that acyl chlorides were very reactive. This is because they contain 2 very electronegative atoms, and so they can readily be attacked by a nucleophile. So moving on to the first reaction, this is a reaction with water. Acyl chlorides react vigorously with cold water, forming a carboxylic acid and releasing hydrogen chloride gas, which is shown as fumes. So here I used an R group to showcase the acyl chloride. It says acid chloride, but it's acyl chloride. So the acyl chloride plus H2O giving you a carboxylic acid plus hydrogen chloride gas. Moving on to the next reaction, this is a reaction with alcohol. So acyl chlorides react readily with alcohol to form an ester and hydrogen chloride gas as well. So as you can see here, the acyl chloride plus the alcohol giving you an ester with both the R groups from the acyl chloride and the ester, and you also form hydrogen chloride gas. Acyl chlorides also have a reaction with ammonia. Okay, now for the reaction with ammonia. Similar to alcohols, acyl chlorides react readily with concentrated ammonia solution. And so for this reaction, I use propanoyl chloride and ammonia to form propanamide plus HCl. So whenever you react the acyl chloride with ammonia, you get an amide, not to be confused with an amine. If I just go here, and the functional group of an amide is shown on the right and an amine is shown on the left. So notice that it contains a NH2 double bond oxygen. For this, with ammonia, you form an amide and hydrogen chloride gas. However, this isn't the only reaction. Unlike with water and alcohols, a further reaction occurs. Since the reactant is a base and the product is an acidic gas, these reactants will go together to form ammonium chloride. So the reaction is NH3 plus HCl, giving you NH4Cl. So if I were to write this as a whole equation, it'd be R plus the functional group of an acyl chloride, which is C double bond OCl, plus 2NH3, giving you the amide, which is the C double bond O NH2 in the R group, plus NH4Cl.
So by now, Yasser has covered 15.13 and Sharvis has covered 15.14. Now I'll be taking on the spec points 15.15 and 15.16. Now before I start talking about the hydrolysis of esters, you need some prior knowledge. Now you've learned this last year and before last year, so I don't think it would be too hard. But esterification is when you get a carboxylic acid and an alcohol to produce an ester and water. Now, as you can see from the water at the end, this is a condensation reaction. And since it's a condensation reaction, it can also be reversed and be hydrolyzed. So this is the hydrolysis of an ester. This is where you get an ester and water, and it forms a carboxylic acid and an alcohol. Now, as you can see from the H plus in the middle, this is basically hydrolysis of an ester in acidic conditions. Now, in acidic conditions, the acid is used as a catalyst and does not take part in the reaction. And acids such as sulfuric acid or nitric acid could be used. Now, going on to hydrolysis of esters into a alkaline solution. Now, this is different because it's not a reversible reaction anymore, and instead the reaction goes to completion as the base, in this case sodium hydroxide, takes place in the reaction. So instead of a carboxylic acid being formed, a carboxylic salt is rather formed, and then the alcohol at the end. Now, a big example of this being used is in saponification. Saponification is the process of making soap. So that is where you get a fat. Typically the fat comes from vegetable oils and sodium hydroxide to make glycerol and a crude soap. Condensation polymerization. Do not get this mixed up with addition polymerization, which we have learned last year and the year before. There are two main differences between the both. One main difference is that you could see over here, two monomers actually make up the one polymer. Rather opposed to over here, it's only one monomer making up the whole polymer. And another difference is that over here, for every two monomers that react, a small molecule is formed, and over here you could see it is water. But over here, it gets turned into the polymer. Now, as to how they form, I'm going to use this as an example, which is a diacid plus a diamine, creating a polyamide. Now, as you can see over here, the word di is used a lot. This is as to create a polymer using condensation polymerization. We need two reactive ends, and over here in this case, it's the H's from the diamine and the OH's from the diacids. Now, as you can see over here, the diacids OH reacts with the diamines H, and what happens is then the final polymer is formed. As you can see, there's the other sides, there's going to be more, and an amide link in this case is formed, and the small molecule that is formed is the H2O. So next up, we need to know how terylene is formed. Terylene is a polyester with this structure. Terylene is formed firstly with a diol, as you can see over here, not an alcohol, as two reactive groups are needed. and it's the same with the dicarboxylic acid. The name for the dicarboxylic acid is called terephthalic acid, and for the diol, it is called ethane 1,2-diol. So what happens is the terephthalic acid's OH and the diol's H group reacts with a condensation reaction and forms this polyester. As you can see over here, an ester link is also formed. Thank you for listening to our presentation. We hope you learned about 15D as much as we did.